Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level chemistry exams, and this video is going to focus on an area of chemistry called Born-Haber cycles. And Born-Haber cycles we can think of as basically giant Hess cycles. So it would be helpful at this point if you've had a look at the two videos I put up on Hess cycles. One of them is about enthalpy of formation Hess cycles, the other is enthalpy of combustion Hess cycles. But we're going to focus on Born-Haber cycles, which are just sort of glorified Hess cycles. And the aim of a Born-Haber cycle is to calculate something called the lattice enthalpy. Now, for an ionic compound, the lattice enthalpy is the heat energy released when you make 1 mole of a solid in its standard state and it's formed from its ions in the gaseous state. So, for instance, if you take solid sodium chloride, you would make it from 1 mole of sodium ions in the gas phase and 1 mole of chloride ions. And you are measuring the enthalpy change that is associated with this reaction. Now, the reality is that we can't determine it experimentally. There's no experiment that we can design, that will enable us to work out this enthalpy change. So instead, what we use is a giant Hess cycle to be able to do this. And I'm going to take you through this, and then perhaps in a subsequent video, we'll have a look at some more complicated examples. So let's have a look at the Born-Haber cycle for sodium chloride. You always start a Born-Haber cycle with the elements in their standard states. So here we've got 1 mole of solid sodium and half a mole of chlorine. Now it's important that we have half a mole of chlorine, Cl2, because we're going to end up with NaCl at the end, which has 1 chlorine. So it has to be half a mole of chlorine gas. And if we take the sodium, which is a solid, and we atomize it, rather than having solid sodium, we would have gas phase sodium. So we're breaking up the sodium atoms so that they are now gas phase sodium atoms. That's called the enthalpy of atomization. It is endothermic, it requires energy. And in this case, it's 107 kilojoules per mole. And that effectively is just going from solid sodium to gas phase sodium. We're then going to do the same thing to the chlorine, where we're going to take chlorine molecules and we're going to break the covalent bond within the gas phase molecules to give chlorine atoms. So that's the atomization of the chlorine. That's also endothermic because we're breaking the covalent bond. So at this stage we have gas phase sodium atoms and gas phase chlorine atoms. Remember, the aim of this is to get through to gas phase ions. So the first thing we do is we ionize the sodium. And that involves removing an electron. And that leaves you with the 1+ ion. That's endothermic as well. And at this stage, we've got Na+ gas and Cl gas. We now need to add an electron to the chlorine. That's called the first electron affinity of the chlorine. So that takes your chlorine atom, adding an electron to form a chlorine ion. That's exothermic, it releases energy. And we now have our gas phase ions. The next arrow we can add to our Born-Haber cycle is to include the enthalpy of formation of sodium chloride. So if you go back to the beginning, you've got solid sodium and a half Cl2. If you just combine them together, it's the enthalpy of formation of sodium chloride. So here's your sodium, here's your chlorine, stick them together, boom, you end up with sodium chloride. That process is highly exothermic, so we're going down to form sodium chloride solid. And then the last arrow that we want to include on our Born-Haber cycle is the combining of the gas phase ions. So the sodium ion and the chloride ion. And that is what our lattice enthalpy is. sticking these gas phase ions together to form sodium chloride. So at this stage we have a Born-Haber cycle fully constructed. We started with solid sodium and a half a mole of Cl2, and if we go clockwise around our Born-Haber cycle, we eventually end up at solid sodium chloride. And the principle of a Born-Haber cycle when it comes to calculations is that if you do one loop of the Born-Haber cycle, so you end up where you started, the overall enthalpy change would be 0 because you've not moved anywhere. So if I just grab a pen and we add the numbers back into this. So this first arrow was 107. The next arrow was the atomization of the chlorine, which was plus 121. The next arrow was the first ionization energy of the sodium, that was 502. The next arrow was the first electron affinity of the chlorine, which was minus 355. Now normally the aim of a Born-Haber cycle is to work out the lattice enthalpy, so let's just call this X, and that's what we're going to try and find out. And then lastly, the enthalpy of formation is minus 411. And the logic, as we've already said, is if you start at the elements in their standard states, which is here, and you do one loop of the Born-Haber cycle, you end up back where you start again, so the overall enthalpy change is 0. And the basic rule here is that if you go with an arrow, you add it, and if you go against an arrow, you subtract it. So starting here, we've got 107 plus 121 plus 502 plus minus 355 plus whatever X is, but we know it's negative. And then lastly, you're going against the enthalpy of formation arrow, so it's minus 411. So minus 411, and all of that equals 0. And therefore X must be, when you work it out, minus 786. So all of the arrows added together should add up to 0. Pay attention to the signs as well. So we know that the lattice enthalpy must always be negative, so you should come up with a negative answer at the end. And that's how we tackle a Born-Haber cycle. Anyway, I hope that was helpful. If you've enjoyed this video, if you found it helpful, remember to like, remember to subscribe, share, keep checking back. At some point I'll put together some videos with some more complicated Born-Haber cycles on them, but for now I hope that was a helpful introduction to the topic, and I will see you next time. Thanks everyone.